later as well when we have more time.
Right. I did open up the floor, but now I'm taking back the floor because I need all the time I can get before I dash off. So, and of course, you know, we don't have, if I can't fit it in, then obviously we can resume next week because there will be multiple parts to this lab. Anyway, so my recording did capture all of the first few minutes, so don't worry, it'll be cut off, and that way the recorded lecture will just have lab 2, so that when you're perusing, you don't have to skip the first 3 minutes or so. Okay, so we're going to departure a little bit from semiconductors and metals to electrochemistry. We'll come back to the lab 1 topics in lab 3. There's going to be a lot of material science concepts that will, I think, hopefully is reviewed for you in this lab. But to start, I'm going to go over the outline because there was some discussion of whether or not we're going to have lab the 26th due to the Career Expo. We will. And for the, I think 3 of you said that you're thinking about going and maybe you'll go right before or right after class. And for the person who may have an appointment during our class time, we'll get to that at the end of class. And then, you know, you can discuss with your lab mates and such then, you know, how you want to handle the distribution of work and what you need to get caught up on. So the breakdown of the lab will be as follows. So this, today we're going to be, you and your group will choose the active material in your battery. There will be several options and they're listed in your procedures already, except for one, lithium nickel oxide will have to be done next week. Electrode fabrication, because it takes a little bit of time to dry, so we're not going to be running the electrochemistry today. Then next week, you're going to be performing the electrochemical testing, so you're going to be assembling your cell, fabricating your electrode, punching out your electrodes, and then assembling your cell, and then testing it, and all the setup procedures also in your procedure handout that's already uploaded on Carmen. And then week 3 will be a repeat, but you have a second material that you can either fabricate in week 2 and then test iteratively, or you can pick one material and test different conditions. That I'll leave up to you and your group. Reminder, fall break, so we won't have class October 10th, and then post-mortem characterization of your cycled battery cathode, okay? So that's the general gist. And I just wanted to go over to Carmen and make sure that everyone is aware that the documents are all here. So if you ever have a question about the lecture, your procedure, hopefully you've looked at it already. It was uploaded a few days ago. Worksheet, because I know some of the calculations, maybe you're not as familiar with the units. Maybe you're comfortable, fine, great, extra practice for you. And of course, additional papers, a seminal paper on lithium cobalt oxide from 1981. And then there's a lot of resources out there in terms of showing you the whole procedure at an industrial scale, at a national lab scale. You know, what you're going to be doing I would say would be, you know, testing a material as if it were you're discovering for the first time. So it's very much lab grade. And then these videos will show you what it's like once you have a compound that you think, okay, this is going to be very efficient, it's going to hold a lot of charge, and how do you scale up? Basically, you know, what would the Panasonics of the world do, or the Samsung, and so forth. So that's all these resources here, okay? So let's go back. All right, so, okay. It seems to not want to proceed. So one moment, let's see. Let me exit out of this. Sometimes the play option is interesting. That's code. Okay, let's start at resources. So, as I've mentioned, there are plenty of resources out there. We'll talk about, you know, not only the material selection, but also failure mechanisms. What happens to a material as the battery is degrading? What does it mean for something to actually be a battery. So it rests on a lot of thermodynamic and structure concepts that have already been covered in your structure of characterization course or thermo course, your structure and characterization lab, because we'll be using the one of the diffractometers at CMAS. And then, of course, everything that you know and love about the intro course and basics of phase diagrams, reviewing your binary phase diagrams and such, okay? All right. So if you wanted to know what should I get out of this lab, here it is. Ultimately, we would like for you to understand the mechanism of charge storage. What does it mean when I say a lithium-ion battery? That you're storing lithium ions, you're storing chemical energy and converting it to electrical energy. Essentially, what does that mean? And how do people report the functions of a battery? You know, if I gave you a voltage curve, can you tell me what are the components, the terminology, and also how to read such a plot, right? Because if you're going to go into this field, these are some of the things that you need to know. And all your learning objectives, and this all you'll carry out throughout the 4 sessions of the lab, okay? So I won't belabor the point. You can read all those points in your lecture slides. Okay, so roughly this is how it's going to be. We're going to define some terms. You know, what does it mean to be a battery? You know, a galvanic cell, electrolytic cell, that sort of thing. How do we judge a battery? What are the figures of merit? Description of what an electrochemical cell is. Fabrication. So we'll go into the procedure itself. You know, we'll talk about safety, and then of course how does one cycle a cell? Okay. So there are many terms for, you know, many definitions for what a battery is. One electrochemical cell typically is not a battery, but you know, the common vernacular these days is that it's used quite interchangeably. So electrochemical cell is also a battery, or it can store charge. But really, a battery is an electrochemical storage device that converts chemical energy into electrical energy, right? That's it. And we'll discuss the metrics of how to judge a battery, like how it performs via its voltage and capacity. And we'll go over how one calculates that from the thermodynamics of a material. And so there are many ways to describe a battery. You know, there are other conditions, like what temperature are you charging at? You know, what's the hysteresis like? What's the configuration? Is it a coin cell? Is it an 18650? I mean, there's many more descriptors, but as your intro, if you're not familiar already, these are the 2 main metrics we're going to stick with. Okay. Okay, so we are going to cover here lithium ion batteries, and there you go. Lithium-ion batteries, because as you can see here, if you plot specific energy, how much watt-hours can you store per kilogram of your active material, divide on the x-axis, and on the y-axis is your specific power, that's watts per kilogram. You can see why we would be interested in understanding these materials, right? High specific energy, high specific power. And you can see where we've come in the battery field, right? You have your nickel, cadmium, lead acid, which is still in cars right now. You have nickel metal hydride. Stanford Ovchinsky worked a lot on this. There's now A123's been pioneering, working on lithium iron phosphate with carbon. And of course, what's not on this axis is a newer technology. It's about 10x, so it's about over here-ish. It's 2,500 watt-hours per kilogram. That's the lithium sulfur. So if you've been reading the news and you've heard of lithium sulfur, where instead of a lithium transition metal oxide as the cathode, you now have sulfur, which is a byproduct of refineries. I mean, you can find mounds and mounds of it, and it's relatively cheap as compared to these active materials. So there's a lot of research and R&D in industry around these materials, but for Lab 2, we'll focus on lithium transition metal oxides, okay? Okay, so let's go through some of the definitions. Voltage is the electric potential energy It is what you've learned in your E&M class, not much more to it than that. In terms of calculating the capacity or the stored electric charge in your battery, you've noticed that sometimes it's it's by gravimetric, so it's per mass, and we'll have to define per mass of what, right? Is it only your active material, the entire mass of your battery itself, including the container, per mass of what, right? So we need to be specific about that. And the way you measure and calculate capacity is just the current times time. So it's basically current integrated over the time that you've applied that current. And then the energy in units of what you would typically expect, joules, whatever, is just the voltage times the capacity, right? So it's just volt times your amp hours, and that's just conventional units, okay? So all pretty standard definition for computation. And this is also in your worksheet, so you can practice with an example. And we'll go through an example here. So let's say you have a commercial, let's say a coin cell, one of those button cells that you can buy, right? Let's say it's a little bit bigger, not really for watches, those are smaller. Let's say you have a big one, and it's rated, and you see the rating at 3.5 volts and 85 milliamp hour. Okay, so you want to know how much energy does this battery store, right? So some of the typical units that you're probably more familiar with would be joule, right? You're probably familiar with joule as an energy term. So we've defined previously that energy is just the volt times capacity. So you know that's 3.5 volts. The capacity is already rated at 85 milliamp hour. We convert that to joules, and you get some abstract number, this 1,071. Okay, great. All right, what does that mean to you? What does 1,000 joules mean to you? It's probably not much. So then let's compare it to another unit that you're maybe more familiar with, the kilowatt hour, right? So you probably have seen this on electric bills, right? That's how they charge you. So you can convert that 1,000 joules through dimension analysis, and you get some small number, 3 times 10 to the negative 4 kilowatt hours. So pretty standard arithmetic so far, just converting. What does this number mean to you?
Pretty low.
Pretty low. Okay, so you're right. It's one coin cell. Pretty low, right? So what is it going to operate? Do you think it's going to operate electric vehicles, say? Right. I mean, that's obviously an extreme example. The answer would be no. Okay, we'll come back to other descriptors here. So let's put it into context, right? If you are thinking about, let's say you're Elon Musk and you're thinking about electrification of vehicles, well, you now have to think, well, how many batteries? Because Mason has said it's very low. How many of these low energy batteries do I have to put together to be equivalent to, let's say, 1 gallon of gasoline? Well, a gallon of gasoline has about 35 kilowatt hour of energy, roughly, okay? And of course, your combustion engine is not perfect. So let's say it operates at 20% efficiency, okay? Well, that means to get about 7 kilowatt hour equivalent, and we were computed the energy of that one battery as 3 times 10 to the negative 4 kilowatt hour, you end up having to need this number of batteries, okay? So you can imagine now this becomes part of your chassis, and now you have to think about it as a structural component beyond just charge storage, okay? And this is your reality, by the way. When you buy a Tesla, this is your reality. But it's actually fewer because they're 18650 and they store actually more than 3 times 10 to the negative 4 kilowatt hour. But it's still in the hundreds, if not thousands, okay? So I hope that gives you a better sense of how much charge storage there is relative to something that you may know and use every day. Okay, so can you get yourself one and a replacement? Absolutely. And only for $1,300, a 7% saving. But when you look at this, you can calculate for yourself if something is rated as it should be. So this is a little redundant, but you can see it's rated as 24 volts, 250 amp hour, and redundantly, they also given you the energy, right? 5.3 kilowatt hour, and supposedly that's 444 Panasonic batteries. So if you do the calculation yourself here, 24 volts, 250 amp hour, convert that to joule to kilowatt hour, it's okay. I mean, within the margin of error, because obviously if you have many batteries talking to each other, you're going to have some ohmic losses and all of that. So sure, it's on the right magnitude, order of magnitude, right? But it really should have about 6 kilowatt hour. But I should say they do actually give you some sense that this is the estimate, because if you look at the fine print, it's about 250 amp hour and about 5.3 kilowatt. So I guess it's 5.3 plus or minus 0.7, I guess, by this calculation. Okay, so these are rough estimates just to give you a feeling of what kind of scales you're working with here. Okay, so we went from one cell. This is what you're probably going to get when you make your own cell versus when you assemble all this to power an electric vehicle. Okay. Okay. One of the other metrics that is quite important is the discharge and charging rates, or the C rate. Okay, and the convention is C over N or C over X. You'll see sometimes, and it's the number of hours required to discharge the entire capacity. You know, that's stored, the capacity that's stored in this battery. So and in your worksheet there are examples. You know, for a 1 amp hour cell, if it's 1 C, you're delivering 1 amp over 1 hour. Okay, so, and if it's C over 2, you're delivering half of that over 2 hours. Sorry. So N is the number of hours. So 2C is in 30 minutes. So that's actually faster. So this is the metric by which people discuss these terms, the rate of discharge and charge. Sometimes people will just give you the current rate. So they'll just say we charge at 0.5 milliamp per gram. So they'll actually just give you the rate, and then you don't have to convert, because you don't have to then know what the capacity is. You can just plug in the applied current, and that's fine too. Okay. And of course, the rate matters, right? Because you can charge a phone very slowly, or you can charge it very fast. But what you'll find is that if you discharge very quickly, you have a lot of ohmic losses, and your capacity won't be as high. So in designing batteries and how they fit into devices, you have to balance between the user experience and how annoyed people are going to be if they have to charge their phone for 20 hours or 2 hours, right? And how weighty your phone or your mobile device, your laptop, what have you, is going to be, right? So you're always playing a balancing game. Obviously, we want more energy, we want more capacity. Yeah, that's great, but are you going to are you going to pay the price in terms of having a weightier device? I don't know. I mean, this is what you have to think about. Okay, so let's dive into the mechanism real fast. Okay, so the mechanism, components of an electrochemical cell. You have your cathode, you have your anode. So upon discharge, you have these green lithium ions going from the anode to the cathode. And you can see here, I've chosen this cartoon to be a layered structure for a reason. So if you looked at your materials choice or the lecture slides that was updated, you'll see that the lithium transition metal oxides that we have are layered type materials, R-bar 3M. And then upon charge, you transport the ions back from the cathode to the anode. And this is a repetitive process. Okay. So the half reactions that occur at the cathode, you can see here, cobalt is going from 3+ to less than to some 4+, right? So if you moved all of the lithium ions out, let's say X equals 1, then you have cobalt oxide, COO2, and that's a +4 state. And that's the reduction potential there. In commercial cells, the anode is graphite. In your cell, which will be called a half cell because it won't be graphite, it will be lithium chips. This will be your anode, right? And this we set at 0, but really the real 0 is the standard hydrogen potential. So it's really offset quite a bit. Okay. So to calculate the open circuit voltage, that's your E0 cell right here. It's just the difference between the potential of your cathode and the potential of your anode. And we're setting lithium as our new 0. So essentially, this is your open circuit potential. in an ideal case, right? Obviously, it's going to be lower because it's not an ideal world. If you were a commercial cell and it's versus graphite, then you just have to take into account that you have to subtract out the potential of your anode, which is really 0.2 versus lithium. And lithium is offset by 3.01 volts versus the standard hydrogen potential. So you end up with something a little bit less. Okay, but very close to what we call zero, which is now our lithium oxidation potential. Okay, so standard, hopefully that was a review from Gen Chem, half reactions. Okay, so if we think about, let's say we have a lithium anode, so we're not concerned about graphite, okay? If you have this reaction here, you can calculate the theoretical capacity of this material by relating Faraday's constant and the molar mass of your active material. So here, if you're transporting one lithium ion, you're transporting an equivalent 1 mole of electron, or 1 minus charge, okay? So you can calculate that. So N is just 1. Faraday's constant is F, okay? Oops, sorry. Molar mass, I'm defining it as molar mass of lithium cobalt oxide, and you should be very explicit about that, and not just cobalt oxide, okay? Or the mass of your cell altogether. So convert that to, convert that to amp hour, because those are going to be the typical units that we work with. So it actually should be milliamp hour. So times 1,000, you get something that looks like this. Okay. Obviously, you're not going to be putting in 1 gram of lithium cobalt oxide. That's going to be a very thick pellet that you have, okay? A very thick electrode. So your mass loading will most likely be 10 milligrams, 20 milligrams. Okay, I mean, even that's thick for commercial cathodes. So you're going to have to scale it by the actual capacity in your cathode, right? This is 273 milliamp hour per gram. So if you multiply that by, let's say your mass loading is 0.01 grams, you're expecting what? 4 milliamp hour per gram in your cathode. That's the capacity, okay, in your cathode. And let's say you want to discharge this or charge this in 10 hours. What's going to be your applied current? Current is what is the unit of current? Okay, but you have milliamp hour. So how does one get from milliamp hour to milliamps? Yes, it is that simple in terms of arithmetic. So yeah, so you divide that by 10, and so let's say, you should be applying, okay. And then there's also coulombic efficiency. So your discharge capacity divided by your charge capacity, and that ratio is reported as a percentage. Okay, so pretty simple. And you'll see that there's actually capacity loss due to restructuring of your material. Okay, I want to make sure we stay on track here. But you can also do this in your worksheet for practice, and obviously during the session today, because you're going to need to figure out all these numbers before next week when you cycle your battery. Okay, and there's also an Excel spreadsheet that's been uploaded on Carmen. The value, you can input your values, but there's no equations because that's a task left for the reader. Okay, so let's talk about how structure relates to thermodynamics, and also how how your voltage curve relates to what's happening in your cathode itself. You know, what is happening in terms of phase transformation. Okay, so if you remember from thermo way back in the day, if you have A plus B going to some product AB, let's say you have a lithiated compound and now you delithiate, or you have a compound like cobalt oxide and you're lithiating it, right? Those are your two species, and you end up with a lithiated or a delithiated state, right? Like the half reaction that I just wrote before. So it's just a chemical reaction. And the Gibbs free energy of that reaction is just the formation of the products minus the free energy of the reactants. Okay, formation energy of the reactants. So it's pretty simple. Hopefully this is a review. So when you have an open circuit voltage, you're not applying any current yet. You've just assembled your cell and you hooked up your electrodes and you're reading a voltage. What does that actually mean? Well, what that actually means is all of this. Okay, so we're going to relate the open circuit voltage to the thermodynamic properties, specifically the Gibbs free energy. Okay, and what's really nice about this technique is you can get thermodynamic variables like your chemical potential straight from just reading off your voltage curve. So you can just do the experiment and you can measure this term, the thermodynamic term, like straight up. Okay, so what does that mean? So let's look at, let's say, a curve that looks like this, right? If you have this sort of profile, once you cycle your battery and you're lithiating or changing the concentration of your lithium and you read your voltage curve like this, what it's telling you is exactly the slope of your Gibbs free energy plot as a function of lithium concentration. It's just the slope of that curve. So it's just delta G divided by delta X. So that gives you your chemical potential, and you can really chemical potential to the voltage, right? The voltage is your measurement. So if we say, let's say the chemical potential of lithium is 0, it's metal, you have a large vat of it, your lithium chip that you're using, it's going to be this infinite supply relatively to what you have, okay? And to the amount of lithium that's in your cathode itself. So the voltage is related to the chemical potential and your Gibbs free energy just by, fundamental equation of state, okay? So then what happens when you have, let's say, a two-phase region? If your voltage curve looks something like this, if you remember, if you have one phase alpha, the other phase beta, let's say here you have no lithium, and here you have fully lithiated, you can see here you have the common tangent, right? Yes. Okay, so this is your two-phase region right here, right? So if you see something like this, you should expect a two-phase region. Right, you should expect some sort of phase transformation because you start out with one phase and then you have a second phase. Okay, so now what happens when you see something more complex like this? What's indicating that there's a stability of a third phase, some intermediate phase, and then you have two common tangents right here. Okay, so whatever you measure directly goes back to the thermodynamics of your system. So I've shown you what ideal curves look like. Then there's reality. Okay, then there's going to be your cathode. Your voltage profiles may not look so simple. So here is a pretty flat region. That seems, like I think we can all agree that that's relatively flat. That's a plateau, right? But then there are regions that look sort of like this. And of course, the dip in voltage isn't always as sharp as what I've demonstrated. Okay, so your curves will most likely look like that. And you can see here with real data, cell voltages as a function of the percentage of a capacity discharge. You can see for different materials, you can see they behave differently. So you can see, okay, there's a two-phase region here, there's one phase, here's, something that looks like one phase-ish. It's like this forever sloping. And what you expect at one cycling rate might not be reproducible for different cycling rates. So for a different C rate, right? Because we talked about thermodynamics, but we haven't talked about the kinetics of it all. just yet, right? We haven't talked about Fick's law and how diffusion affects how lithium ions go through your material. So if you nanostructure your active material versus not, they do behave differently. And so there's thermodynamics and kinetics built into these electrochemical cells. Okay, so how does voltage change as a function of composition? So here's an example of lithium cobalt oxide, and this was taken from this seminal 1981 paper that you should read about. This is the paper that started it all, by the way. So if you've ever wondered, how long does it take fundamental science to translate into commercialized technology, here's the date for you. Although it's relatively fast because I think Sony commercialized it in 91, so it was actually only 10 years. Okay, so what you have now is built on this. Okay, so you can see here your voltage is changing as a function of X. Okay, so we've already covered how voltage relates to the K3 energy and your chemical potential. Okay, and then for your charging curve, this is the lithium cobalt oxide charging and then discharging curve, so charging this way and then discharging coming down here, okay? And sometimes it's reported like this. So you have capacity here. You can also report number of moles of lithium that's equivalent to the capacity. People sometimes report both because sometimes you just want to work off of the stoichiometry versus like what does 50 milliamp hour per gram mean? It's sometimes easier just to work off of stoichiometry. Okay, so let's go over your lab procedures and how you're going to actually carry out the analysis of your pristine cathode and also the cycled cathode, okay? So what people typically do is they'll start off with some active material here. You see all these powders and that Katrina have already put out back there for you. So today, instead of using this fabulous high-speed mixer, you are going to be the mixer, and you're going to be using these beautiful mortar and pestles that will also be back there. And you're going to assemble a slurry. That slurry will be used to cast electrodes, okay? You're going to coat that onto carbon-coated aluminum foil. And then next week, you'll assemble in the glove box, and then you can cycle. But for this week, this is going to be you. So some elbow grease is going to be needed for this week. Okay, right. So once you assemble, which will be done all in the glove box, as you can see here, then you can cycle. Then you can take it out. This is an argon glove box. Does anybody know why we don't use a nitrogen glove box? Yes. What's the product? When lithium and nitrogen meet. Lithium nitride. Exactly. The lithium chips that that you'll get, you'll actually have to polish it a little bit onto the little cleaning pad that's already in the box that Katrina placed there. So, we'll go over all that procedure, but it is an issue. Oxides and nitrides are, it's going to be an issue for lithium conductivity. So that's something to keep in mind. Now, the coin cells, you're probably used to this configuration. What you're going to assemble is a more simple, simpler configuration that you see here, and that's mainly because unless you've used a glove box before, it can be quite tricky to make this assembly without shorting your cell, okay? And here I have a configuration of a Swagelok cell. These are Swagelok parts from John Goodenough, right? The inventor of the lithium cobalt. So, just put two Swagelok parts together, your current collectors, and you're good to go to revolutionize history. So that's pretty exciting. Okay, so the structures that you'll be working with, right? Lithium cobalt oxide, R-bar 3M, this is the pristine. You also have your choice of C2M and this Benel lithium manganese oxide. So you have a choice. Lithium nickel oxide will be coming. So you need to know what is your starting crystal structure and how is that going to change? And where is it going to change? Where would you expect to change based on our discussion just now? In your voltage, what would you expect to see? In terms of a change in your voltage profile? Deep thought, I see. Okay. Well, when you get into your group, you can discuss as a group what you should be seeing and where you need to stop the cycling. Okay, so I'm going to go over some failure mechanisms quickly because we can have that discussion next week. We can pick up on it if there isn't time. Actually, there's a little bit of time, so I'll go over that. Okay. When you're thinking about material selection, you need to think about, what's the band gap of my material? Do I want something that's more electrically conductive, ionically conductive? Should that be a concern of mine? You should think, okay, cobalt could be magnetic. Is that something I should be concerned about? Phase stability, when you delithiate and lithiate, when you remove these compounds, the intermediate phases, how stable are they, right? And also, if you haven't heard of this term yet, the solid electrolyte interface, it is both the bane of your existence and the reason why batteries work at the same time. Okay? These interfaces right here, what typically forms when you're making, when these batteries are being cycled, if you haven't already learned this from Professor Meyer's class that's concurrent to our lab, what typically forms is you have these, you have your cathode, you have your anode, and you have your separator. This plastic separator is drenched in an electrolyte, which is a salt in a solvent, right? So this electrolyte you'll be using is commercial 1 molar LiPF6 in ethylene carbonate dimethyl carbonate. Okay, so you can imagine this salt being highly corrosive, reacting with lithium, as well as reacting with your lithium cobalt oxide or whatever lithium transitional oxide that you choose. It's going to form this interface that will allow lithium ions to be transported. But what is this interface at the interface, right? And it's dynamic. Every time you charge, discharge, it will change. So knowing and identifying the components for one cycle does not really mean it's going to be the same intermediate species going forward. And it's the dynamics of it actually makes it really interesting to study, but also makes it difficult. So there are in situ characterization techniques. Basically, you make your battery, but either with a hole milled through your battery cell, so you can do X-ray diffraction or neutron scattering or X-ray absorption or TEM or SE, I mean, you name it, or Raman spectroscopy, so that we can try to understand what's happening as you cycle the battery. And that is of interest to basically all electrochemists, because if you can control this, you can control a lot of the mechanisms of failure and prevent them. Or you can understand what's actually positive and advantageous about having this layer there. But control is key. We know it's there, but understanding what forms and how we control the formation is the heart of a lot of people's research. Okay, so in terms of understanding failure mechanisms, you don't have to, explore all of these mechanisms because obviously we're a little bit limited in terms of X-ray diffraction for this lab. There are other techniques as well, and if we had, let's say, a whole year to do this, or 5 years of a PhD, or a lifetime career, that sort of thing, we can absolutely do everything under the sun, right? But we have one lab session for postmortem analysis, so we're going to stick with X-ray diffraction. You can have many things that happen during the cycling of a battery. One of the most deleterious reactions is when you transport lithium ions. They don't plate. The ions don't plate in the same way. You could have started off with a beautiful planar lithium chip, and then as you redeposit, you can have dendritic lithium that forms, and then as you can expect, if the lithium grows and grows and touches the other electrode, you can imagine the short circuiting that happens. And of course, we've all seen all the reporting that has happened at the $2 billion cost scale in terms of that failure mechanism, what happens there. And thermal runaway is another issue, okay? So there's a lot that goes on in terms of not only designing the material, so that's going to be the focus of this lab course, which is the cathode side, but obviously there's quite a bit of work still being done on the anode selection, electrolyte design as well. So there's a lot. And of course, who's to say you have to work in carbonates? Can you get salt water to work for you? The answer is yes. You can also do that. So there's a lot. There are numerous ways in terms of implementing charge storage, and so this lab will just focus on one of them. But hopefully that'll give you, a preview into the vast world that is charge storage. Okay, so any questions, comments? Yeah.
So we're going to be cycling our cells until they fail by this mechanism?
No, I really hope we don't get to that point where you short circuit your cell. Let's try to avoid that.
How many times are we going to cycle the cell?
That's a great question. You and your group will decide that. So we have the cycler, we have the potentiostats basically from when we have lab all the way until Monday 9 a.m. So for starting next week. So we can decide, how that's going to operate. So you can decide your conditions. If you want to do one long scan, stop in the middle of a plateau, or fast cycling. So I'll go into greater detail as to the number of cells you have, but essentially it's going to be 2 cells per group per week, and you have 2 weeks of cycling. So basically you have total 4 cells. So essentially that means 4 conditions. Okay. So in terms of operations, I think it's probably best that we just start with the slurry mixing. If you've read the procedure, you'll know that we are adding in the lithium transition metal oxide of your choice, the carbon additive, so it's more conductive because these oxides are inherently not great conductors, and a polymer binder. Okay, and you're going to be doing 2 styles of electrode fabrication. One is casting, where you're doctor blading the slurry and forming a beautiful, nice film. And then the second one is just loose powder that will pack together. Okay, so with that, I think we're ready to begin. Oh, Katrina has a comment.
Wayne, does he have any students to help break down the lab codes for you, since you will be working with chemicals? You have lab codes and property.
Right.